Okay, so the general thing of an alcohol is an alkanol. Remember, the alk is just a prefix holder for the number of carbons. So it's your meth, eth, prop, etc., depending on how many carbons are in your chain of the alcohol. The suffix changes because the OL is the alcohol, is what that part is referring to. Right, so remember this is different than, let's say, an alkane in the general way that there's no alcohol. So the alcohol is ROH. Alkane just has carbon-carbon single bonds, right? So the difference between the alkane and the alkanol in terms of the naming convention is you drop the E and add OL for an alcohol. So a specific example is, let's leave it like that. But this would be chiral, so let's make it not chiral. Okay, so here's our alcohol, and again, your first thing is longest chain. So here it doesn't matter which direction we go, if we go left to right or right to left. Either way, we have 7 carbons as our longest chain with the alcohol at the 4th position. So either way, this is going to be a heptane. And then we drop the E and add OL for the alcohol, which is this functionality here. And it's located at the 4th position in the chain. So this would be a 4-heptanol. Right, so we'll do one more example, a little bit more challenging one in this case. So here we have a chiral molecule because there's no symmetry across this bond, for instance, or across the horizontal because the symmetry is broken. In this case, because you have the OH that is different from this methyl group. And then across here, you have the methyl group and just hydrogens on this side. So this is chiral. So you have to include the absolute configuration in the name. So we'll have to determine that. So we'll do that last because we can determine the rest of the name without knowing the absolute configuration, but we just have to remind ourselves that that has to be included or the name is incomplete. So first, we need to determine the longest chain. We either have a branch of 1 carbon or we have a 6-membered ring. So the 6-membered ring is definitely the longest chain. And now the question is, where do we start our numbering system? Well, generally, functional groups have priority in terms of the lowest number over substituents. So we would want our functional group, which is the alcohol in this case, to be at the lowest number that it can be. And with this molecule, it's going to be 1. That's the lowest position because we can start our numbering system anywhere. So we can start it at the functional group. So now from there, we have to number it clockwise because if we were to go counterclockwise, we would put our first branch at 5. Instead, we can put it at 2 if we go clockwise. So this is better going clockwise because it puts the number at 2, which is lower than 5. So here we have a methyl group at 2 methyl. This is a cyclo group because it's cyclic. There's 6 carbons, so it's cyclohex, and they're all single bonds, so it's a cyclohexane. And we drop the E and add OL for our alcohol, so it's a cyclohexanol. So now if you put this all together, excluding the stereochemistry, at this point, it would be 2-methyl 1-cyclohexanol. Or you'll see this as well. This is not my preference, but it is becoming more and more common where you add the 1 in between the ane and the OL, or whatever the number is for the alcohol. In this case, it happened to be 1. But in either case, this is incomplete because you have to consider the stereochemistry in your answer. If you don't, then the name is somewhat ambiguous. So here, what we need to do is determine, is this R or S? So I'll just draw a new molecule down here so we can determine that without the clutter. All right, so let's start at the top one. It makes no difference where you start. So this carbon here, highest priority, we have a oxygen, carbon, carbon. So oxygen is highest priority. Now we have a carbon and a carbon, so we'll have to compare further. So this carbon is bound to 1 carbon and 2 carbons in the hydrogen, and this carbon is bound to 1 carbon and 2 hydrogens. So the carbon that has 2 carbons bound to it is a higher priority. So this is 2 then, going clockwise away from the oxygen. So then this is 3, and our hydrogen's in the back. So this looks like R. The hydrogen is in the back, so this is R. So we would call this position R, and it's 1. The position is 1 by our naming convention. All right, so now we have to do the same thing at the second position. Well, try to save time, but that made it more difficult. Okay, so if we look at this one, we have a carbon, carbon, carbon bound at that chiral center. So we don't know what has priority based on the first atom, so we have to move to the next atom. So this carbon is bound to 3 hydrogens. This carbon is bound to a carbon and 2 hydrogens. And this carbon is bound to a carbon and an oxygen. So the one with the carbon that's bound to the oxygen has highest priority. So this is 1. Then the carbon bound to another carbon is 2. And the methyl group, which is just bound to hydrogens, is 3. And the hydrogen's in the back. So it'll be what it looks like. And it looks like S. So it is S. So this is 2S. So now the only way of reporting this name correctly is using parentheses between the chiral centers. So 1R, 2S, then it's the whole name. So 2-methyl cyclohexanol. Or you can put the 1 between the methyl and the cyclo. Doesn't make a difference. Either one would be acceptable and correct. So questions on that? That's kind of a nice review of absolute configuration, which will be definitely on the exam. All right, so moving on, we'll talk a little bit about the physical properties of alcohols. So first, alcohols can have hydrogen bonding, which is a key characteristic when you compare physical properties of these two molecules, for instance, alkane versus an alcohol. So this can have hydrogen bonding. And like we talked about last time, hydrogen bonding is very specific. So what we mean by that is it needs to have an extremely electronegative atom that's bound to the hydrogen that is then hydrogen bound to another extremely electronegative atom that also has a hydrogen. So what I mean is you need to have a hydrogen bound to a nitrogen, oxygen, or fluorine. It can be any one of those that's in proximity to a hydrogen that is bound to another nitrogen, oxygen, or fluorine. This is a hydrogen bond. The reason we define it this way is these have the highest hydrogen bonding, because remember, hydrogen bonding is just a specific dipole-dipole, and we call it a different thing because it's much more stabilizing compared to dipole-dipole. So in order for you to assess relative boiling points or melting points, it's good to be able to identify if they have hydrogen bonding or dipole-dipole, because that's going to tell you directly which molecules would have higher or lower boiling points. So the case with water or with alcohols, which are similar to water, is that you have these OH bonds that can hydrogen bond to another OH, right? You get a network like this. So again, this meets our criteria because we have a hydrogen that's bound to an oxygen that is in proximity to another oxygen that is bound to a hydrogen, right? If you were to consider, I don't know, let's say acetaldehyde. So this would not be a hydrogen bond, even though it looks like it, right? So this is a hydrogen interacting with an oxygen, but this hydrogen is bound to a carbon, and that oxygen is not bound to another hydrogen. So at most, you would define this as dipole-dipole, whereas this is hydrogen bonding. So if the question was rank boiling points or melting points, this would be much weaker. This is weaker IMF, intermolecular forces, which is what we talk about with dipole-dipole. So that would have a lower boiling point. It would take less energy to break these bonds since they're weaker. This, on the other hand, is a stronger intermolecular force, so it would have a higher boiling point. I don't know the numbers offhand, but I would imagine, you know, water is 100 degrees C, so I would imagine the alcohols are like 70 or so. Whereas these groups would be, this might even be a gas at room temperature. So that would mean that its boiling point is less than 20 degrees C. Now, if you compare this to just the alkane can only have dispersion forces, right? There's no dipoles at all in the molecule. So this is going to have a boiling point of like -80, right? So you don't need to know the numbers by no means. Like, I'm not even sure the numbers I'm giving you are accurate. I'm just giving you, it's all relative. But if you had to rank the boiling point order of this versus this versus this would by far have the highest. This would be next, and this would be last in this order, based directly on this has H bonding, this has dipole-dipole, and this has just dispersion, London dispersion. Right. So there's also some other physical properties associated with alcohols. For instance, the oxygen and the hydrogen can either be basic or acidic, respectively. So that can be taken advantage of in synthesis and other approaches. So before we get into that, are there any questions about the intermolecular forces and how it relates to boiling points? All right, not seeing any questions. We'll move along. So, like I said, this dipole exists between the oxygen and hydrogen. So the oxygen is partially negative and the hydrogen is partially positive. So that means that this hydrogen is weakly acidic because it has a weakly positive charge, partial positive charge. So the pKa's of alcohols in general, and this is a number you should definitely know, so have it memorized, but this works for any alcohol. It's approximately 15 to 16, you know, somewhere in that range. The reason we know that is because pK of water is 15.7. So this is of water. So the structure of water in an alcohol is pretty similar. So their acidity is also pretty similar. However, you should know that this is by far a weak acid, right? If you're going to compare it to like HCl or HBr, HCl's pK is definitely negative. I don't know the number exactly, but it's like -2, let's say. So remember, these are log scales. So the difference between a pKa of 15, even let's go on the lower side, and a pKa of -2, that's not a 17 difference. That the difference between these two is 10 to the 17, right? So that's a bunch, you know, that's a billion times a billion almost difference in terms of acid strength. So basically I'm just reiterating, like, know that. So I mean, this applies with like pH too. A lot of people will be like, you know, your pH of your soda might be like 2, and the pH of like battery acid or something is like half. So a lot of people are like, that's not that different from battery acid, the soda that you drink. Well, again, the difference between these two is 10, well, almost 10 squared. So it's almost 100 times more acidic the battery acid is than the soda or whatever acidic drink that you're drinking. So when people make those claims, they're not understanding that this is a log scale, which is exactly the same with pKa values. So if you're going to compare, I mean, even if you compare like an alcohol to a phenol, and a phenol is this. So benzene alcohol, this is a pKa of like 10. So again, this is 10 to the 5 difference. This is 10,000 times more acidic than the alcohol. So anyway, that's just to remind you of what pKa is measuring and the relevance there. So, but now that's not really related to the overall point, which is this is acidic, weakly acidic, which that point has been made, but it is still acidic enough that if you have a strong enough base, you can abstract this proton. So one of the most common bases to do these types of extractions is sodium hydride, which is this. So now let's talk about the difference between a hydride, a hydrogen, and a proton really quickly. So this is a hydride. Hydride is a hydrogen with a lone pair. So it's s orbital or full. And that's why it gives it a negative charge, because our formal charge counting, hydrogen would only want one valence electron to be neutral. So that's why the neutral hydrogen, this is just a hydrogen atom, is a radical, because it has just one electron, and that makes it have a formal charge of 0 because it's because of the formal charge counting. And then this is a proton because it has no electrons and just one proton and one neutron. So we just call the ionized positively charged hydrogen atom a proton, because in essence it is just a proton. There's no electrons around. So this is a hydride, which means that it can function as a base or a nucleophile. In this case, it's going to be a base because there's no electrophilic center really. So anyway, we have sodium hydride. This could abstract this proton. And then we've done acid-base chemistry before. So this just gives you the conjugate base. Now this conjugate base is called an alkoxide. You should know that because you'll see like sodium methoxide, for instance. Well, this is specifically sodium methoxide, what I've drawn here. So ethoxide. Again, the alkoxide, the alk is just a placeholder for the number of carbons. So in this case, we have 2. So it becomes F, and then it's oxide because the oxygen is charged negatively. So this is useful because let's say you wanted to turn your alcohol into a good nucleophile. So you can do this in like one pot synthesis where you just put your sodium hydride in first, and then that's going to make your negatively charged alkoxide. And then you could react this with like alkyl chloride that you wanted to do your reaction with. That's going to get you your ether now, because your first step is getting you this, and then the second step gets there, right? Because this negative charge will attack this position and cleave the chlorine, right? So That's why we bother with knowing about the acid strength, because you can use bases to turn your alcohol into a more useful molecule for your synthetic procedure or whatever. Okay, questions about any of this? All right, so now the next thing is that oxygen is basic, right? Because we still have this dipole, same dipole, but there's a partial negative charge on the oxygen, which makes that basic. Which means that a lone pair on the oxygen could attack an acid. So for instance, if you react this with HCl, you could get this protonation event. Right? And now this looks like water, right? This H2O, that's one other R group. So this is now a good leaving group. So you can do other chemistry with that. So it doesn't have to be HCl, by the way. It could be lots of acids. But let's revisit E1. Because remember, I basically always said that E1 is associated with SN1. It's like a byproduct of an SN1 pathway, which is usually the case. But you can do these dehydration reactions with alcohols that, depending on the identity of your acid, you won't get any of the SN1 product. So let's look at an example. All right, so if you react this with H2SO4, you will only get the SN1 product, or you will get no SN1 product. You'll get only the E1 product, which is this one. Okay, now the question is why? Well, it has to do entirely with the structure of H2SO4, so we need to look at that. So H2SO4 is this structure. Right, because the sulfur is bound to the four oxygens, right? So that would give you the double bond oxygen, and then single bond to the other oxygens that are OH groups. And these are the acidic hydrogens, which is why we put them in front to remind you of that. So you may be wondering, how come sulfur has an expanded octet? Sulfur is in the third row, so it has access to the d orbitals, so it can have an expanded octet, and that's why this is the structure. This is the most stable. If you were to draw any other configuration, the oxygen would be charged, or the sulfur would have a lack of an octet, or etc. So this is the best structure that fits all of our normal considerations when we look for stabilized structures. So what's going to happen here is these are extremely acidic protons because you have extended induction effects based on the sulfur. Also, this conjugate base is stabilized, right? Which is our primary rule when we're considering acid strength, because here's a conjugate base. This conjugate base can resonate into this oxygen, right? You can go here and then up there, or it can go here and then up there. So it's extremely stabilized, the conjugate base is, which means that the proton wants to leave a lot, so it can make that conjugate base that's so stable. So that's what will happen. This oxygen will function as a base, pull off this proton, and get the conjugate base. So here's your product, conjugate acid of the alcohol, protonated alcohol. And then you have your sulfonate, which is this thing, the conjugate base of the sulfuric acid. Right, I drew it the other way just to illustrate a point, but it's identical. So What's going to happen at this point is this is a good leaving group now. So this will spontaneously cleave, just like we see in our unimolecular reactions. We're going to form a carbocation. And this is somewhat favored because that's a tertiary carbocation. So there's no issues there. So now you might be wondering, well, we have a negative charge and a positive charge. Why doesn't this just attack the positive charged carbon and get to SN1 product? Well, this is a terrible nucleophile. It's a terrible nucleophile because it's so large, right? This sulfur is bound to 4 oxygens. There's a bunch of electron density there. So it makes it very difficult for that negative charge on the oxygen to approach the carbon in such a way that the SN1 product will form. So it doesn't form at all. What does happen is you get the E1 product in which this proton can be abstracted by the carboxylic, by this conjugate base, and then you get the E1 product, which is here. So it's much easier for this oxygen to approach just a hydrogen as opposed to this center that is very substituted with methyl groups and etc. And this hydrogen could leave spontaneously. It doesn't have to be facilitated by the conjugate base, but this last step occurs so quickly, it's difficult to argue which, if it's a spontaneous leaving of the proton or if it's abstracted. So both are acceptable, but it would definitely be wrong to consider the conjugate base of the sulfuric acid to be a nucleophile. That's the takeaway. It's definitely not going to be a nucleophile. But let's say you did the same reaction with HCl. Well, Cl minus is pretty small. It's kind of a weak nucleophile, but it's not a terrible nucleophile. So it could easily attack the carbocation. And in that case, you would get SN1 and E1. So sulfuric acid is useful for a non-nucleophilic acid for these types of dehydration reactions. All right. Questions on the basic nature of the oxygen atom of a alcohol? Okay. Now we'll talk about how you can convert an OH group into good leaving groups. And there's a bunch of ways to do it, but there's really 3 that you should like have in your toolbox, your synthetic toolbox. Basically, you'll need to memorize these ones because they're the most commonly used and most useful. So you can convert any alcohol into a great leaving group in 3 main ways. You can turn it into a chloride in 1 step. You can turn it into a bromide also in 1 step, or you can turn it into a tosylate, which is something that you're not familiar with, I'm sure. But we'll talk about what the structure of a tosylate is. But this is effectively just a good leaving group, just like the halides. So to turn it into a chlorine, you want sulfonyl chloride. To turn it into a bromine, you want phosphorus tribromide. And to turn it into a tosylate, you want tosyl chloride. Okay, so you need to know these reagents. So I'm just going to show them to you now, and then we'll go through each one next. So let's start with the tosylates because those are probably the one you're least familiar with out of these 3. So that's what we'll start. So a tosylate looks like this. And this is why we use an abbreviation, because this structure is somewhat complicated. So this is tosylic acid, the one with the OH. And then tosyl chloride is the TSCl. So this would be TSOH. Right, so effectively this whole group here is TS. And then what's bound to that sulfur is what oops, not capital, it's lowercase. It's not a transition state. Yeah, so what's drawn here is what's bound to that sulfur. So tosyl chloride then, again, this whole structure, and then a chloride instead of an OH. So then when you react this with a alcohol, you end up with this group. Right, where this whole thing is an excellent leaving group. Super good leaving group. Because the tosylic acid that we started with up here has a pKa of about -4. So this is an extremely strong acid, which means its conjugate base, which is this, is extremely weak. Remember, good leaving groups are extremely weak bases. So this is an excellent leaving group. So that's kind of the whole point here is you can convert an alcohol, which is a terrible leaving group because OH is a strong base. So you can turn this into a good leaving group by reacting with tosyl chloride. So you get OTS, and then you can react this with, you know, some halide or some nucleophile, let's say azide. So this can attack, and you get the alkyl azide, right? Because if you tried to do this in one step, react this with just the azide, this doesn't work because the alcohol is a bad leaving group. So you need to go through the tosylate first, and then you can do your nucleophilic substitution. So that's probably all you'll need to know about tosylates. You should be able to recognize the structure, but I doubt that you will have to draw it from scratch. But if you see it, you should know it. All right. Now, you don't need to know the mechanism of conversion for any of that. I didn't even show the mechanism because it's an acyl substitution mechanism, which is something we haven't talked about yet in class. So you won't be responsible for the mechanism, but you'll need to know the reaction change with the tosyl chloride specifically. So let's look a little bit at the chloride one now. So sulfonyl chloride, which is SOCl2, looks like this. Oops. Right. So the first step in the mechanism is this is going to attack here. You don't need to know this mechanism either. But the important thing to note is that the reason I show this first step is because this is different. This is very different than if you were to react this with HCl, let's say. Because if you wanted to do this with HCl, you could hypothesize that you could attack here. You get this, right? Then this could leave. Then you get this, and then the chlorine will attack, and you'd get this. Well, there's a bunch of problems with this because my specific example, this is a primary carbocation, which is never going to happen. So this is not going to happen. But even if it wasn't a carbocation, even if it was not a primary carbocation, even if it was secondary and it was feasible, whenever you're forming a carbocation, you always have to think about rearrangements. So you may not get the product that you want because if you're going through this method, because the carbocation is very labile, it's going to react extremely quickly. And if there's a more stable state that it can exist in, it's going to. So the point of why this matters is SOCl2, the first step doesn't involve any protonation. It's just a nucleophilic attack at this electrophilic center. So all of this is SN2. So this is going to get your conversion with high selectivity. right? So that's the point. If you try to go through this one, you may get selectivity. It just depends on the alkyl halide. But if you use SOCl2, you're always going to get the position that the alcohol will be substituted with the chlorine, which is the same the same exact reasoning for the bromine. This will get you this, right? And again, the mechanism in the first step involves nucleophilic attack at the phosphorus now, like this. So that's why you get the selective position. You don't get any rearrangements or anything like that. All right. Questions about any of that? All right, so for the last little bit, we'll talk about oxidation reactions of alcohols. So let's look at this example. So you can oxidize with harsh conditions, which are things like the Jones reagent. The Jones reagent is chromic oxide, I believe is the name of this. But this will oxidize all the way up to the carboxylic acid. So if we consider this carbon's bound to one oxygen in our alcohol. It's bound 3 times to oxygens in the product, so it has increased its oxidation state twice, provided by this chromic acid, which has a structure like this, which I doubt you'll need to know, but it's similar to H2SO4, except there's a chromium instead of a phosphorus, or instead of a sulfur. But let's say that you don't want to get the carboxylic acid. You want to instead get the aldehyde. Am I missing carbons? 1, 2, 3. No, okay. So you can do that also, and you can do that with a mild reagent like PCC. And you may need to, again, you won't need to have the structure memorized, but you'll need to be able to recognize it if you see it. So this is pyridinium chlorochromate. So pyridine is this structure here. And then pyridinium is the protonated version of pyridine. So that's pyridinium. And then chlorochromate is Cl floating around, and then chromate is that. So due to the nature of this, you'll end up with stopping at the aldehyde. So this won't give you the carboxylic acid. So you'll definitely need to know the differences there, because depending on what any synthesis question would be asking, you would need to be able to recognize that what reagents you would need to facilitate that transformation, whatever the specific question was. Okay, so let's say that you did this on a secondary center though. We started with a primary alcohol, but if you did this with a secondary alcohol, it makes no difference what reagents you use, you get the exact same product. All right, if I did this with Jones, you get the ketone. If I do this with PCC, you get the ketone. Because it's impossible to oxidize further because you have the methyl groups that block it, right? Right. If you tried to make this into an OH, you would have to get rid of a carbon, which you can't. You just can't do that. So in this case, it wouldn't matter if you had a secondary center. Now, let's say you had a tertiary center. well, none of this oxidation is possible if you have a tertiary center. If you do this with Jones, the hypothesis would be this type of structure where you just oxidize to like a ketone-like thing, but this has 5 bonds to your carbon. So that's never going to happen. All right, so this doesn't happen. So no oxidations on a tertiary center. All right, questions on oxidation? Okay, you can also reduce to form alcohols. So this is now the opposite of the oxidation that we were just talking about. You can go from a carboxylic acid to the primary alcohol by using lithium aluminum hydride, or LAH. This will give you the alcohol. You can also reduce this to the aldehyde if you wish with DIBAL, which is diisopropyl diisobutyl aluminum hydride. So let me think. So we got so it's that, and then there's a hydride, well, just one hydride, and that's what's providing the reduction. Okay. What else? I guess that's it, right? Yeah, that would be it. Right. So you could reduce the ketone, I guess, is another way you can look at this. The ketone can be reduced. In this case, just use lithium aluminum hydride is the easiest to use. You don't have to. DIBAL is only specific if it's necessary, but here it is not necessary. You just get the alcohol. It's like the similar situation with oxidizing the secondary alcohol. All right. Questions on reduction? All right, and the last thing we'll talk about is a Pinacol rearrangement, which is a super cool reaction. So this goes from this is called a vicinal alcohol, diol, to a ketone. And this is done under acidic conditions. So I'll just say H plus to not be specific, some acidic conditions. And you may wonder, how do you even begin this? Well, it's not trivial to look at it, right? This is a difficult question if you're asked to draw the mechanism, but you can kind of envision, like, just do some counting here, right? So we have 1 methyl group here and 3 over here, right? If we look at our starting material, we have 2 methyl groups here, 2 methyl groups here. So obviously one of them has to migrate from one side to the other side, and the side that it migrates to loses the alcohol. And then the side that it migrated from is now becoming a ketone, right? So that can guide you a little bit. So now, first we have an acid and we have basic centers, right? So our oxygen, one of these oxygens is going to function as a base, okay, and attack that proton. So that's what happens first. Okay, now this is a good leaving group, so it can freely leave. We get a tertiary carbocation at the end of that, so that's favorable. That's okay. And we get here. Okay, now we can have, this is the part that's tricky. So now you can get a methyl shift, and you may wonder why. Why does this methyl shift happen? Well, after this methyl shift, you get a secondary. You get a secondary carbocation, right? So you're like, why would this happen, right? You go from a tertiary center to a secondary center. Well, this is resonance stabilized because you have this lone pair here. And this will, because of this resonance stabilization, this can happen. So when this resonance stabilizes, you get this, which is almost your product. Now you just, you'll do this in like methanol or something. You'll have some solvent that's basic. So I'll just say ROH. And this will pull off the proton. And now you're at your product. So that's a pretty definitely a challenge question for the exam. I'm not sure. It's in the textbook, which was a little bit surprising to me. But I don't think you might need to know some part of the mechanism or something to that aspect, but I don't think you would have to draw it completely from start to finish like I just did here. But know about it because it'll come up in some way. I wouldn't be surprised since it was in the, or it is in the textbook. So, questions on any of that? Anything today?